Let's see the next practical on neural network. So today we will train our model on image data set, and the image these are in grayscale, means you will have the value from 0 to 255 for each pixel value. So the data set that we are going to use, that is Mnist Data Set. In that data set, total 70,000 samples are there. And what is this Mnist data set? It is handwritten digit data set, and that is from 0 to 9. So total 10 digits. And such 70,000 samples we have. So first task is to load this data set. So here we will use this keras to import the Mnist data set. Once we import that data set, then we will divide this data set in train and test. This is the inbuilt function load data, which will load your data into X train, Y train, X test, and Y test. You need not to train and split the data set. So let's do it. Once we have this data, X train, Y train, X test, Y test, then after that we can use those data set. Let's first print the shape of train and test. So you can see here your X train that have 60,000 samples and your test has 10,000 samples. So out of this 70,000, 60,000 for your training and remaining 10,000 for testing. Now see the remaining two dimension, that is 28 comma 28. So what is that? So this shows the image size. So we have 28 cross 28 images, right? So we have this image 28 cross 28. So how many pixels we have? We have 28 cross pixels. So we have image. So means in this image you can have 0 or 1, 2 up to 9, any value, right? So such 70,000 samples are there, and out of those 70,000, 60,000 training and 10,000 for testing. Now the task of neural network is to correctly identify this image, whether it's 0, 1, 2, 3 or 9, means from 0 to 9, right? So we want to train for that. As we have seen in the previous practical, that is iris data set, we had a 4 columns. Each column is a feature, and we are directly giving those values like x1, x2, x3 and x4. These are the features, and we are giving those features as an input to neural network, and then we are classifying it into any 3 classes. But here we have an image, right? So let's first see the image. So I'm just showing you the image of one example. So this is the picture of that 0, right? And respective label is 0, right? So what we have? We have image and respective label. So the images, those are in X, and your labels are in Y. For this image, the label is 0. So in X train 1, right? This is 28, 28 means all rows or columns. So this is the first image, that is 0, and respective label is 0, right? And we have divided this data. Now, if we remember the previous practical for 3 class, right? What we have done, we have converted the label into one hot vector, right? We have converted into one hot vector. So we need to convert the labels from 0 to 9 into one hot vector. So what will be the vector size? The vector size will be 10 elements, right? Out of those 10 elements, there will be one at a respective index. Means for label 0, the one hot vector representation will be 1 and rest of 9 will be 0. So this is one hot vector, right? So this is your output. This image is your input. But still, how can we give this image as an input? Right? So that is a question mark still. We'll see later on. First, we'll convert this label into one hot vector. So in Keras, we have two categorical function that is used to convert these labels into one hot vector. Right? So I have converted those labels, that is in y train and y test, and that is converted into one hot vector. So let's see for that example one hot representation. So you can see here 1 and rest are 0. So this is one hot vector. So this is your output based on image. This is your output, right? Now next, we have values in the image from 0 to 255, as this is a grayscale image. Now this is somewhat larger value. We cannot say complete very large value, but to make our algorithm work faster, we will normalize it. Sometimes if you have more features and they are in different range, then also you need to normalize your data. Here, just for simplicity, we are normalizing our data. So what we are doing, we are normalizing the data from mm, minus 0.5 to plus 0.5. So you can see here your x train divided by 255 minus 0.5. So what is the maximum value? That is 255 for each pixel, right? This operation will perform pixel wise for each pixel. So 255, that will be the maximum value for any pixel. So 255 divided by 255, that is 1, minus 0.5, that is 0.5. The minimum value is 0 for any pixel. So 0 divided by 255, that is 0, minus 0.5, you will get minus 0.5. So this is the range. So the image value, this each pixel value, that will be converted, the range will be converted from minus 0.5 to 0.5 instead of 0 to 255. We have converted it. Still, this is 28 by 28. The shape is this only, right? Okay. Now, next, the question is how to give this image as an input to neural network. as neural network, just accept the vector representation. So what you need to do, you need to convert this 2D matrix into vector, vector of 7, 8, 4, 28 cross 28, right? So it will give you a vector of 784, 784. Now this 784 that represent each pixel means there are 784 pixels in this images. 7, and each pixel, right, re- given as an input to neural network. And how many such pixels are there? 7, 8, 4 such pixels are there. So to neural network, what we are giving for each image? 784 pixel value, right? 784 pixels we have. The value of each pixel from minus zero point 0.5 to zero point 0.5, that will give as an input to neural network. So this is your first network, right? How many? 784, and this is your input. This is your input, right? Okay, so we have normalized our data, and this is just to showcase that normalization one, right? So 0 that is converted into minus zero point 0.5. Then what we have done? We are converting this 28 cross 28 images into vector of 784, right? So your X test train norm, we are reshaping it to 784. Same way X test we are doing reshape, right? So each will be converted into 784 vector. Now before this, the X train size of X train or dimension is 60,000 comma 28 comma 28, right? After this reshaping or converting into vector, that is 28 cross 28, the new shape, that is 60,000 comma 784, right? So we have converted this 2D matrix into vector 784. Then you can see here Y train encoded shape. So before encoding, we have just a label from 0 to 9, 0 to 9. So for Y train, we have 60,000. You can see here, we have 60,000 labels, right? We have 60,000 labels. Now we have converted that labels into one hot vector, and each vector size is 10. So this will be converted into 60,000 comma 10. Same way, this will remain same for test, just the sample size will be different. So 10,000, 10,000, right? So we have now ready with our data, that is our input and our output. Now our next step is to construct the neural network. So as you know, this is the sequential model. As we are stacking the different layers and we are implementing fully connected network, so we will use this dense. Then first we will initialize it, model equal to sequential. Then this is the first hidden layer. How many neurons are there in first hidden layer? So hidden layer 1. Oh, there are 64 hidden layers, and we are adding these hidden layers, right? So how this hidden layer knows that there are 784 inputs? So you need to specify this input underscore beam, that is 784. We'll consider that there are 784 inputs in first hidden layer. And for this layer, activation that we are using is ReLU activation. Then we are adding the second hidden layer, and the number of neurons in that are 32. 32 neurons are there, right? And the activation function that we are using is ReLU. Here you need not to specify the input because this is a second layer. Only at the first layer you need to specify the input dimension. Then last is our output layer. In output layer, we are classifying into 10 classes 0 to 9. So there will be 10 neurons at the output layer, and the activation function, that is softmax, right? Because it's a multi-class. If you're single class, then you can use sigmoid or softmax. After initializing this, what you need to do? You need to compile your model, right? So let's compile the model, and we are specifying categorical cross entropy, right? Because we have multi-class and optimizer, as I have said. If you don't know, then you can go with Adam, but you can see the changes in your result by giving different optimizer value, right? Then metrics, that is accuracy, and then we'll see the model summary. So first hidden layer, second hidden layer, and output. And how many parameters are there? 2650, right? So I will calculate. So weights are for this 64 multiplied by 784 plus 64 for bias. Same way you need to calculate at here, you need to calculate it here. If you add it, then you will get total number of parameters, that is 52,650, right? Okay. Once we compile the model, let's train the model. And what we are doing, we are giving train, x train and y train, the vector 60,000 comma 784 and 60,000 comma 10, that is one hot vector representation of your label. And epochs, we are using 20 epochs. These are the trainable parameters or hyperparameters, you can say, epochs and batch size. And batch size is 16. Let's train it. What you are seeing here, 3750. So it indicates how many batches are there of 16, right? So if you divide 60,000, that is your total number of samples in training, by 16, then you will get 3750, right? And we have kept 20 epochs in there. This shows your training loss and training accuracy. This is during the training, right? We are not testing it right now. So in previous one, we have direct features to be given as an input, but here we have image. So first we have converted that image into vector, and then we have given that image as an input, right? And the output that we have converted into one hot vector. And we have also calculated the total number of trainable parameters and how to calculate those trainable parameters that I have shown. Now our model is trained on our training. Let's see the testing accuracy. So on X test and Y test, we will test it. So our accuracy, that is 97.70% accuracy that I got using this model, right? So this way you can train your neural network on any black and white, means grayscale image. Now the question arises that what about the colored image? So if this handwritten data set, if this is a colored image, then you will have the third dimension, that is channel, that is your uh, RGB, red, green and blue. 28 cross 28 cross 3, this dimension will be of your image, right? So what you need to do, you need to convert this 28 cross 3 into a vector, and then you need to give that vector as an input to neural network. But this is not that much if each you can say effective, because the image can have a spatial information, means pixel here will have some information or dependency on pixel over here, here, right? So this is called a spatial information in image. So CNN gives you a based result, right, which is a one type of neural network only, involves convolution in that, right? So that we'll see later on. So here in this spectral we have seen how grayscale image that is converted into a vector and given as an input, and then we have a output. Now if you want to utilize the weights that you get after training, right? So what you can do, you can save those weights, right? Whose weight? This model weight, right? So our model name is model only, model dot save weights, and dot h5 we are giving in this. So it will save the weights of this model in this. After that, whenever you want to use these weights, first you need to construct the model. So this way you can construct your model, and after that what you can do, you can use this call like model dot load weights, so it will load the weights, right? You need not to train it again, and after that you can predict on your example, right? So this is your practical. Now what you do, what you need to do in this practical is you need to see the effects of tuning hyperparameters like running rate, if you change if you change epoch size, if you change batch size, right? Take different values and observe the accuracy. So what this will give you impact on your training and testing. Then you need to see the impact of number of hidden layers, right? We have two hidden layers with size 64 and 32 and one output layer. So you can change the number of layers, like hidden layers. You can change the neurons in each hidden layers and see the output. You should also check the impact of activation functions and dropout. So here activation functions we have used, that is ReLU. You can see the effect of different activation functions in this, like in terms of accuracy, in terms of speed that you can see. You can also see the effect of dropout, right? So when some uh, you are getting very good result during your training, very good accuracy, and then when you test it, you don't find a good accuracy. Means your model is overfitting to your data. So in that case, you can use this dropout, right? So once you check this, you try it with this different values, right? You observe those values and then take this data set, it is fashion Mnist, right? The description of that data set and all that is given in this link, in this link. So you need to check and perform your neural network training in this, right? Okay, thank you very much.